LearningMeasure.tv, science and engineering podcast with emphasis on measurement. Brought to you by David Archer and LearningMeasure.com. Episode 8, Introduction to Statistics. Hello, I'm David Archer, owner of LearningMeasure.com and LearningMeasure.tv. This podcast is sponsored by TradePub.com, GoToMeeting.com, and is part of the Blueberry community of podcasts. Well, haven't done one in a few weeks. I don't know if you can tell from my voice, I'm still a little bit sick. Last few weeks I've had a really bad case of bronchitis, so I wasn't able to do these. Plus my day job sent me off on a business trip for a week, so that's why I'm a little late in getting the next one out. I'm going to do something a little bit different than what I planned for this week, for this next podcast, just because I think it might be a good idea based on some people's comments and what I plan to do in the future to go over a little bit different topic before going back to what I was planning on doing. And this week we're going to do a little fundamental talk about statistics and probability, probably this week and next week, and then use that for something that I want to do in a future podcast. Okay, first of all, I want to talk about what is a statistic. You know, it sounds funny. People think they have some sort of magical meaning. A statistic is nothing more and nothing less than a number that characterizes a set of numbers. Now, the set of numbers could be discrete or continuous, but in any event, it's a single number that is used to characterize a set of numbers. One example of statistics for discrete data is the number of data points, n. That is one that, well, you need to know for actually computing most of the other statistics you're going to compute about a set of data. Well, we're going to talk about one in particular now, well, actually several. One is the mean. Let's say you have a bunch of data. We'll call it xi. Okay, a data set, discrete data, labeled by the index I. The mean of the set of data is the sum of I equals 1 to n. This is one of the statistics, the number of data sets, of xi, well, divided by n. Of course, the n could be outside, but I'll just put it here for now. This is the mean. This is the mean. Now, there are some terms in statistics that you might hear. Population, and sample. Okay. Population, just basically the whole ball of wax, all the data that you could possibly ever get for a given thing you're trying to measure or look at or whatever. And a sample is just some part of it. Example of why you might want to sample, maybe if you were trying to measure the, I don't know, something that if you actually measured it, destroyed the thing you're trying to measure, which sometimes happens. In which case, the population's all the things you made, and you want to take a sample of the population to test to see if this thing is what you think it is. Because if you did the whole population, you'd have no product. Well, the mean of the population is usually given the symbol mu, lowercase Greek mu, and the sample mean is usually written x bar. Okay. Does the mean mean anything? Well, no, it's just this mathematical operation. It doesn't necessarily mean something in particular. In fact, the meaning of what the mean is, it depends on where the numbers came from, the underlying process that you're measuring So you can't assign, say a mean has any particular meaning unless you know, or any other statistic for that matter, has any particular meaning unless you know something about the underlying process. Well, actually, more precisely, it has a meaning. You just have to interpret what that meaning is requires understanding of the underlying process. I'll give you an example. One of the things the mean is sometimes used for is to eliminate variability in a process. Let's say you had 10 people measuring the length of a rod. Well, if you expect that each measurement is in error by some random amount due to variations with the way people measure it, then the mean might give you take some of the variability out of the process. But let's say your data set looks like this. Okay. Let's say this data is reading off a counter that's counting seconds. The mean of this data set doesn't have that meaning. It doesn't take anything out of the variability. In this case, all the mean tells you is something about your patience level. Okay? It isn't necessarily the case that the mean has a specific meaning. It depends on what the underlying data represent and what distributions they come from. Okay. The mean is an example of something called a measure of central tendency, a measure of the middle of your data set. It isn't the only measure. One example is called the median. You may have heard terms like median income on television or median house prices. Median isn't all that difficult a concept. Median value is the value which exactly half of them are greater than it and half of them are less. Let's say you have a data set of like this. It's 22, let's say 2, 5, 12, 15, and 30. Okay. The median value of this data set, since there's an odd number, is 12. That means exactly half are below it and half are above it. There's equal number above and below. What if we added another number here? 1. We've got an even number. What's the median? Well, by convention, what is usually done is you take the middle two values. So there's 1, 2, 3, 4, 5, 6 values. So what's usually done is you take the middle two values, take their average. So this is 17 divided by 2, right? So that's going to be the mean, 17 halves. Or sorry, the median. So exactly half the data is below it and half the data is above it. That's the median. That is another measure of central tendency. Well, what other measures are there? Well, there's actually a whole bunch that you might see. One is mode. Mode is an interesting concept. Mode, in a discrete data set, the mode is the data that shows up the most often. Let's say you have a data set that looks like this. 1, 5, 5, 10, 12, 13 or something. Well, this value 5 comes out the most often, so that's the mode of the data set. What about this one? Here, 5 and 7 appear just as often in this data set. 2 5s, 2 7s. There are two modes for this data set. This is called a multimodal data set. There's more than one mode. It also applies to continuous data sets, continuous distributions. You know, and if you look at like your famous bell curve that you may have seen before, the mode is the most probable value, which would be the peak. But if you had a distribution that looked like this, it has two modes. Again, a multimodal distribution. So that applies to both continuous and, in this case, it may not be considered so much a measure of central tendency, but it can be. Okay, but there are others. One example is the geometric mean. You have a data set, xi again. Well, if you had this, the nth root of x1 times x2 times xn, that's called the geometric mean. So where does this come in? Well, example might be is if you're measuring data in dB and you do an arithmetic mean of the value in dB. Well, what that really is a geometric mean. So it does occur in measurement situations. It's another measure of central tendency. Well, there's another one I want to talk about real quickly. There's another one called a harmonic mean. Harmonic mean is I equals 1 to n of n over 1 over x. Sorry, that's wrong. Do this again. N over the sum over I equals 1 to n of 1 over xi. Harmonic mean. Well, there are places where you could use this. In fact, you might notice that this is really the form of when you add resistors in parallel, it's basically 1 over n times the harmonic mean of the resistance values. But there's other reasons you'd use the harmonic mean. We'll just deal with that later. Okay. Before we get too much farther, I got to pay little bills. So, if you're looking for a better way to present or collaborate during your conference calls, your solution is simple. Web conferencing with GoToMeeting. During your call, everyone logs on to GoToMeeting.com and your computer screen shows up on their computer screens. It's like you're in the same room. GoToMeeting is perfect for sales or product demos, training, or real-time collaboration. Plus, you're not charged per minute like other providers. You can meet as often as you want for as long as you need. With GoToMeeting, you can meet with anyone, anywhere, without leaving your office. You'll not only save time, but money too. See for yourself. Try GoToMeeting free for 45 days. Just visit gotomeeting.com/podcast. That's gotomeeting.com/podcast. Try GoToMeeting today. Okay. Well, now we've got some idea of the center of your data set. You might want to know something about the spread of your data. Well, one simple measure of one statistic that measures the dispersion of your data is the range, which is the largest value minus the smallest value of your data set. The next one that's used a lot is what's called the variance. Variance is defined as, well, before I get to the variance, you might think, well, maybe you might want to measure something like how far it is from the mean. Well, you might think, well, what about the average distance from the mean? Let's try that as a measure. See what that does. So the average measure for difference from the mean would be this. Well, you sum up the average distance from the mean. Well, this is equal to this. It's the sum of I equals 1 to n of xi over n minus the sum of I equal 1 to n, because I'm just breaking the sum up, of x bar over n. Okay. Then, well, this here, that's x bar, minus, well, this is n x bars divided by n, this x bar equals 0. Okay, maybe that's not such a good measurement of the spread of the data set. Well, the next thing might be try is the average square. That's non-zero. But that's not typically average square deviation from the mean. Now, this is non-zero. It is a measure of the dispersion of the data, but what's typically used is n minus 1, and I won't get into why in this episode. So this is called the variance, or sigma squared. Now, if you wanted a difference between, if this was the population, this would be mu, or if the sample, this is x bar, it's still the same thing. So variance is the sigma squared. So sigma, which is the square root of this, is called the standard deviation. Which equals this, square root of it's called the standard deviation. The reason why you use this is because this is the same units that your data is in. This is in units squared. And so if you want something that's in the units that you're measuring, you take the square root of it. And then again, this is called the standard deviation. What this means does not, again, depends on what your data is. Okay? For instance, the example I gave before of a timer, standard deviation there is also just a measure of how patient you are. It doesn't tell you anything else than that. In the case of measuring a rod, it can tell you something about the variability of people making measurements of the rod. And if you know something about the distributions, it tells you something about the probabilities. Okay. Now, those are all measures of dispersion. Now, there are other statistics that, well, in fact, we talked about one in previous episodes, Allen variance, which deals with time series data, which is another type of statistic. Gives you a measure of the variability on different time scales of an oscillator. But then there's other types of things. You notice this particular measure was proportional to the square of the difference. What about the cube? Well, there's a number called the skew that you can come up from a data set. Skew. Well, this is just, okay, sum I equals 1 to n of xi minus x bar cubed over n sigma cubed. What this tells you is whether your distribution of your data is symmetrical or not. If a nice symmetrical distribution has a skew of 0, a distribution that looks like this has a positive skew, and a distribution that looks like this has a negative skew. It's just something that characterizes the distribution of numbers in your data set. Now, there is also, that's the third power of the difference from the mean. There's also another thing that has a name that's proportional to the fourth power of the difference from the mean. And it has a fancy name. And if anybody knows the history of this, they could send me an email. Kurtosis. It's a strange name. Okay, it's sum I equals 1 to n of xi minus x bar to the fourth power over n sigma to the fourth minus 3, if I got that right. Kurtosis tells you how much data is in the tails of your distribution compared to a normal distribution. A normal distribution is the bell curve you might have all seen before, or maybe you haven't. It looks something like this. But there's some data out here in the tails. So this normal distribution is the sort of the standard. So if you have a distribution that's like, well, let's say looks more like this, so that there's no data out near the tails at all, that would have negative kurtosis. If you had a distribution that looked more like, oh, I don't know, something like that, that would have positive kurtosis. It's got it got more data in the tails than a normal distribution, which we'll talk more about later. Okay, so now we've got all these statistics, which generally may or may not mean anything useful. They all mean something, but they don't necessarily mean what you think they mean, unless you understand the underlying processes. Okay, I'm going to take a little break now, and we'll be right back in a second.
One of LearningMeasure.tv's sponsors is TradePub.com. TradePub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the LearningMeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories and sign up through that link. Each publication subscribed to through this link on LearningMeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support.
Okay, so far we've discussed a lot of statistics. One of the things you need to know if the statistics mean anything is something about probability. We're going to talk a little bit about a probability now, but mostly we're going to talk about probability next week. What is probability? Probability is a number, p, and p is between 0 and 1. The probability of something is the proportion of favorable outcomes divided by the total possible events, for instance, or total possible choices. For instance, flipping a coin. If a coin's fair and each a head and a tail is equally likely, the probability of heads equals 1/2. The probability of tails equals 1/2. There should be no surprise. Okay. One thing you should notice, probability of heads plus the probability of tails equals 1/2 plus 1/2 equals 1. That's something that is true of all probabilities. The sum of the probabilities of all the outcomes has to equal 1 because something happens. Okay? So if you flip a coin and you just discount the possibility it's going to land on its side, or you could even add the probability of landing on its side, let's say. And let's say this was, 1/2 minus some small number, and then whatever the remainder is, you're going to have the probability of something happening being 1. So if you have, let's say, two choices, A and B, in this case, heads, tails, you'd write P of A for the probability of the event A happening, and P of B is the probability of event B happening. And if A and B are the only choices, you must have PA times PB, or plus PB, equals 1. Another thing that you must have is that if there's only possibilities, two possibilities, let's say they're not equal, it must be the case, of course, from this, is that PB equals 1 minus PA. Okay, that's just another this revisited. So say the coin is asymmetric, so that for some reason it's heavier on one side, and let's say there's a 2/3 probability it'll be heads and 1/3 probability it'll be tails. Well, the same thing happens then. The probability of heads is 1/3 or 2/3 and 1/3. So that equals 1. There's another type of probability called a conditional probability. Well, actually, maybe we'll wait for that for next week. Okay, but what about, that's for discrete events. What about continuous distributions, like the height of people? Well, the probability of measuring of somebody being exactly 5 feet tall is 0. Think about that. That means the probability of measuring exactly 5 feet to infinite decimal places is 0. Because it's 1 out of infinity, right? Because there's infinite choices. So there's the probability of somebody being 5 feet tall is 0. The probability of somebody being less than 5 feet tall is not 0. So you can figure out the probability of some, let's say, height less than, well, it's of height less than x, let's say. Okay, you can figure that out. You can just figure out what proportion of the people are shorter than 5 feet. Well, then you could plot that, and you could plot probability of h less than x, and it will probably look something like this. Okay, so where it goes asymptotically to 1, and it starts at 0. So that the probability goes up as you go higher and higher in height. The probability of somebody being 1 inch tall is probably pretty low. But 1 foot tall gets a little bigger, maybe 5 foot tall is over here somewhere. The probability of somebody being 8 feet tall is pretty low. So you're going to have some sort of distribution like this. This is called a CDF, or a cumulative density function, or whatever. So this tells you the number less than a certain number. Now, there are certain points, you talk about percentiles or confidence intervals. If you look here at like 0.25 or something, or 0.1, let's say, if you wanted 90% confidence intervals, you can say, well, you go to 0.9 here, and that would be 90% of the people are less than this number. You can look at things like that. But then you could look at this thing and take the derivative of this. The derivative of this. What does the derivative of this look like? We've talked about derivatives in previous episodes. The derivative of this looks something like this. It's called the PDF, probability density function. And that what represents here is areas under the curve here, let's say this, is the probability of events happening between these bounds. Okay? The bell curve, the normal distribution curve, is a PDF. And so in a PDF, since this is a derivative of this function of probability less than a certain value, to get back to the other one, you integrate. So the area under this curve tells you the probability of the value you're measuring being within the bounds you integrate from. So if you integrate in the tails here, that'll tell you what the probability of being in the tails. If you wanted to know what the probability of somebody being, let's say, taller than a certain value, you pick that certain value and you integrate over here. If you wanted a probability of somebody being shorter than the mean value, which I don't think you can need to do any calculations at all, well, maybe you do. That'll tell you by taking this area here. That's a probability density function. It turns out that for the normal distribution, and we'll talk about what exactly that is next time, it turns out that if you take the mean value, assuming it's symmetric, and you look at plus or minus 1 sigma from the mean value, it turns out for a normal distribution, this corresponds to 68% of the values will measure between 1 sigma. 2 sigma, it'll be like 95%. And 3 sigma, it would be 99.7%. 1 sigma, 2 sigma, 3 sigma from the mean for a normal distribution. You may have heard of these numbers before in terms of like confidence intervals. Well, all this means is you've made the assumption your data comes from a normal distribution. If it hasn't, you have to do something else, and we might talk about that next week. Okay, that's just sort of a whetting your appetite for next week. Okay, that's the basic stuff I wanted to go over. Where I have something in mind of where I'm going to go with this, and I probably will come back to radar when I'm done. I have a reason for that, like we talked about last time, maybe doing radar. But again, if you have some suggestions for what you'd like to see on this, anything at all, send an email to suggestions@learningmeasure.tv. And if you want to be on the show, you want to show some sort of measurement apparatus, or you want to talk about some software, or you want to do, advertise your consulting business, and you're in the Las Vegas area, going to be in the Las Vegas area, first send me an email at vendors@learningmeasure.tv, and we'll put you on. Okay, hopefully I won't get sick again, and I'll be able to actually put out one next week. That's it for now. I'll see you later. Bye.